Welcome to the Deep Dive, where we take a stack of information and extract the most important nuggets of knowledge and insight, giving you a shortcut to being truly well-informed.
Today, we're embarking on a deep dive into the fascinating world of liquids and the fundamental forces that hold them together. We're drawing insights from the textbook, Chemistry, the Central Science.
Right, and our mission is really to illuminate these core chemical principles, explain them in accessible, student-friendly language, and, connect them to real-world applications and maybe surprising aspects of your everyday life.
Exactly. Get ready for some aha moments, hopefully.
Let's start maybe way back with a nod to ancient philosophy. Over 2,400 years ago, Empedocles proposed four fundamental elements: air, water, earth, and fire. What's really fascinating is how his intuitive understanding kind of loosely aligns with the three primary states of matter we're exploring today: gases, liquids, solids.
It's a foundational concept, absolutely. The key differences between these states, well, they boil down to how their fundamental particles, atoms, molecules, ions, whatever they are, how they're arranged, and crucially, how much they can move.
Tell us more about that. How do they differ?
Okay, well, in gases, the molecules are really far apart. They're moving chaotically, super fast, and the attractive forces between them, almost negligible.
So they just spread out everywhere.
Pretty much. A gas will completely fill any container, taking on both its volume and its shape, and they're highly compressible. Think about squeezing air into a bike tire. You can fit a lot in there.
Right, like air filling this room, or if you, I don't know, open a canister of something, it just disperses instantly.
Exactly. Now compare that to liquids. Here, the attractive forces are much stronger, strong enough to keep the particles close together.
Okay.
So liquids are much denser than gases and far less compressible. They have a definite volume, but because the particles can still slide past one another, liquids can be poured. They take the shape of the container they're in, at least the bottom part.
Like pouring water into a glass.
Got it.
The volume stays the same, but it fits the glass shape.
Precisely. And then you have solids. Here, those intermolecular forces are so strong that particles are essentially locked in place. They vibrate, but they don't really move around.
Forming rigid structures.
Yep, rigid structures. And like liquids, they are not very compressible. Because the particles in both solids and liquids are so close together compared to gases, we often call them condensed phases.
Condensed phases, okay. So if we look around us, how does this play out in, everyday stuff?
Well, the state of any substance, solid, liquid, or gas at a given temperature and pressure depends on this delicate balance. It's a tug of war, really.
Between what?
Between the kinetic energy of the particles, which makes them want to fly apart, and the attractive forces between the particles pulling them together.
Ah, okay.
Consider the halogens. You've got iodine, which is a solid at room temperature, then bromine, which is a liquid, and chlorine, which is a gas.
And that's not random.
Not at all. It's a direct consequence of those attractive forces getting weaker as you go from iodine to bromine to chlorine. Stronger forces hold iodine together as a solid, weaker forces let chlorine molecules fly free as a gas.
Wow, that's a really clear illustration. So stronger attractions mean more likely to be solid or liquid.
That's basically it. And pressure plays a huge role, too. Think about propane.
Like at a barbecue tank.
Exactly. At room temperature and normal pressure, it's a gas. But inside that tank, it's under high pressure. That pressure forces the molecules closer together, those attractive forces take over, and boom, you get liquid propane, LP.
Okay, that makes sense. So pressure can squish things into a liquid state. Let's switch gears slightly. Have you ever seen water bead up on a lotus leaf? It's amazing, right? How it just rolls off, cleaning the leaf.
Oh yeah, the lotus effect. It's a fantastic example of what we're diving into next, intermolecular forces.
These aren't the bonds inside molecules.
No, that's crucial. These are the forces between separate molecules. They're much weaker than the intramolecular forces, the actual chemical bonds holding atoms together within a molecule.
Weaker? Okay, how much weaker?
Significantly. For example, it takes about 16 kilojoules of energy to vaporize 1 mole of liquid hydrogen chloride, HCl. That's overcoming the intermolecular forces. But to actually break the covalent bond inside an HCl molecule, that takes 431 kilojoules per mole. Way more energy.
Ah, okay. So boiling points and melting points, they're basically telling us how strong these intermolecular forces are.
Exactly. They're like a report card for intermolecular attraction. The stronger the forces, the more energy you need to pull the molecules apart, so the higher the melting or boiling point.
Makes sense. So what are the main types?
There are three main types we talk about for neutral molecules.
Yeah.
Dispersion forces, dipole interactions, and then a special case, hydrogen bonding.
Let's start with dispersion forces. You said they're in everything.
They really are. Dispersion forces, sometimes called London dispersion forces, exist between all atoms and molecules, even nonpolar ones.
How does that work if they're nonpolar?
Well, electrons are constantly moving, right? So at any given instant, the electron distribution in an atom or molecule might be just momentarily uneven. You get a temporary instantaneous dipole, a slight positive end, and a slight negative end.
Just for a split second.
Exactly. And that fleeting dipole can then induce a similar temporary dipole in a neighboring atom or molecule, like a tiny brief ripple effect. This leads to a weak, short-lived attraction.
Okay, a fleeting attraction. Does it add up?
Oh, definitely. Especially in larger molecules, the strength depends on polarizability, basically, how easily the electron cloud can be distorted or squished.
Squishiness. I like that.
Yeah. Larger atoms or molecules with more electrons tend to have more diffuse, squishier electron clouds. They're more polarizable, so they generally have stronger dispersion forces. That's why boiling points often increase as you go down a group in the periodic table, like with the halogens or noble gases, the molecules get bigger.
Does shape matter too?
It does. Take pentane. It's a long linear molecule. Compare it to dimethylpropane, same chemical formula, C5H12, but it's much more spherical, compact.
That's why.
Pentane boils at 36.1 degrees C, while dimethylpropane boiled at only 9.5 degrees C. The linear shape of pentane allows for more surface area contact between molecules, leading to stronger overall dispersion forces than the more balled-up dimethylpropane.
Fascinating. So even shape influences how well they stick together. What about the next type? Dipole-dipole.
Right, dipole interactions. These occur specifically in polar molecules that have a permanent built-in separation of charge, a permanent positive end, and a permanent negative end due to differences in electronegativity between the bonded atoms.
Unlike the temporary ones in dispersion forces.
Exactly, these are permanent. So the positive end of one polar molecule is consistently attracted to the negative end of another nearby polar molecule. Think about acetonitrile versus propane. They have similar molecular weights, but acetonitrile is polar, propane is nonpolar.
And acetonitrile boils higher.
Much higher. Acetonitrile boils at 82 degrees. Propane boils way down at negative 42 degrees C. That big difference is largely due to the dipole forces in acetonitrile.
Okay, that's a clear difference. And then there's the really strong one. Hydrogen bonding.
Yes, hydrogen bonding. It's a special, particularly strong kind of dipole interaction. It's very specific.
How specific?
It happens only when you have a hydrogen atom that is covalently bonded to a very electronegative atom, specifically nitrogen N, oxygen O, or fluorine F.
N, O, or F.
Got it. That H atom, which is now very electron poor, is then strongly attracted to a lone pair of electrons on another nearby N, O, or F atom in a different molecule.
So H bonded to N, O, or F, attracting another N, O, or F.
You got it. Think about water, H2O, ammonia, NH3, hydrogen fluoride, HF. Their boiling points are incredibly high for their small molecular weights. Why? Hydrogen bonds. They're much stronger than typical dipole or dispersion forces.
And this is why water is so weird, right? Like ice floating?
Exactly. That's one of the most critical consequences. In ice, each water molecule forms hydrogen bonds with 4 neighbors in a tetrahedral arrangement. This creates a very open, crystalline structure.
Open, so less dense.
Precisely. There's more empty space in the ice structure compared to liquid water, where the molecules are closer together but less ordered. That's why ice is less dense than liquid water and floats.
Which is huge for life on Earth if ice sank.
Lakes and oceans would freeze solid from the bottom up. It would be a completely different planet. So yeah, hydrogen bonding in water is fundamentally important.
Now, okay, are there any other forces? You mentioned ions earlier.
Yes, ion dipole forces. These are important when you dissolve an ionic compound like salt in a polar solvent like water.
So between an ion and a polar molecule.
Correct. The positive ion, answedation, is attracted to the negative end of the polar molecule's dipole, and the negative ion is attracted to the positive end. These forces are generally quite strong, often stronger than hydrogen bonds, which helps explain why many ionic solids dissolve well in water.
Okay, so we have dispersion, dipole-dipole, hydrogen bonding, and ion dipole. If you're looking at 2 different substances, how do you compare their overall intermolecular forces? Do you just add them up?
It's kind of like that, yeah. You have to consider all the forces present.
Okay.
Dispersion forces are always there. Then you check, is the molecule polar? If yes, add dipole forces. Does it have H bonded to N, O, or F? If yes, add hydrogen bonding, and that's usually the most significant contributor if it's present.
So hydrogen bonds tend to dominate if they exist.
Often, yes. For example, compare acetic acid and 1-propanol. same molecular weight, both can hydrogen bond. But acetic acid has two oxygens, and it can actually form two hydrogen bonds with a neighbor in specific arrangements, leading to stronger overall attractions and a higher boiling point than one propanol.
And if there's no hydrogen bonding?
Then you look at polarity and size. If molecular weights and shapes are similar, polarity differences, dipole, usually dominate. If molecular weights are very different, the larger molecule, with its stronger dispersion forces, will typically have stronger overall attractions, assuming polarity is similar or absent.
Got it. It's like a checklist.
Yeah.
So these forces dictate so much. Let's look at how they show up in liquid properties, like honey pouring slowly.
That's viscosity. It's a measure of a liquid's resistance to flow. Honey is very viscous. Water is much less viscous.
What makes something viscous?
Primarily strong intermolecular forces. The molecules attract each other strongly, making it harder for them to slide past one another. Molecular shape also plays a role. Long, tangled molecules, like in motor oil or syrup, can increase viscosity.
Like molecular spaghetti.
Haha, yeah, kind of. And temperature matters too. Heat things up, molecules move faster, overcome those forces more easily, so viscosity generally decreases. Hot honey flows much faster than cold honey.
Right. Okay. What about things like water striders walking on water or water beating up?
That's surface tension. It's like the liquid has a skin on its surface.
A skin. How?
Molecules inside the liquid are pulled equally in all directions by their neighbors, but molecules right at the surface, they have neighbors beside and below them, but none above. So there's a net inward pull on the surface molecules.
Pulling them tighter together at the surface.
Exactly. This inward pull makes the liquid try to minimize its surface area. The shape with the smallest surface area for a given volume is a sphere. Hence, water droplets are spherical. Water has high surface tension because of its strong hydrogen bonds.
Makes sense why water beads up on a waxed car. The wax is nonpolar, water is polar. They don't attract much, so water pulls itself into beads.
Precisely. And that leads us to capillary action, like a paper towel soaking up water.
How does that work?
It's a balance between two types of forces. Cohesive forces, which are the intermolecular forces within the liquid, like water molecules attracting each other, and adhesive forces, which are the attractions between the liquid molecules and the surface of the container or material, like water attracting the cellulose fibers in paper.
Okay, cohesion versus adhesion.
Right. If the adhesive forces are stronger than the cohesive forces like water adhering to glass or paper, the liquid will be pulled upwards into a narrow tube or porous material. That's capillary action.
And that's how plants get water up their stems.
Yep, that's a major part of it. Conversely, if cohesive forces are stronger, like with mercury in a glass tube, the liquid pulls away from the walls and you see the surface curve downwards.
Fascinating. Speaking of applications, you mentioned ionic liquids earlier. Salts that are liquid.
Yes, it's a really interesting area. These are basically salts composed of ions, but they happen to be liquid at or near room temperature.
Why aren't they solid like regular salt?
Yeah. Often it's because the ions are large and irregularly shaped, maybe one or both of them. This makes it really hard for them to pack neatly into a stable, ordered, crystalline, solid structure, so they remain liquid even at low temperatures.
And what's special about them?
Well, they have very low vapor pressure, they don't evaporate easily, they're often non-flammable. Many are good solvents for a wide range of substances, and they can be stable at high temperatures.
So potentially greener solvents?
That's a big part of the interest, yes. Replacing volatile, often flammable or toxic, organic solvents in industrial processes or labs, it's a promising area.
Very cool. Okay, let's talk about changes between states, like those instant cold packs or heat packs you use for injuries.
Perfect examples of phase changes and the energy involved. Every time a substance changes, state melts, freezes, boils, condenses, sublimes, there's an energy change.
Energy is either absorbed or released.
Exactly. Melting, solid to liquid, also called fusion, vaporization, liquid to gas, and sublimation, solid directly to gas, all require energy input. They absorb heat from the surroundings. These are endothermic processes.
Like melting ice cools your drink.
Precisely. The reverse process is freezing, liquid to solid, condensation, gas to liquid, and deposition, gas directly to solid, all release heat into the surroundings. They are exothermic.
Like steam condensing on a cold mirror releases heat.
Okay. And the amount of energy involved is specific. The heat of vaporization, for example, is generally much larger than the heat of fusion for the same substance.
Why is that?
Because going from liquid to gas requires the molecules to completely overcome almost all the intermolecular attractions to fly free. Melting just loosens those attractions enough for the molecules to move around, but they're still close together.
Got it. More energy needed to fully escape.
Right. And we can track this energy input versus temperature using a heating curve. If you plot temperature against the amount of heat added to a substance, say ice, you see something interesting.
What happened?
The temperature rises as you heat the ice. Then, when it hits the melting point, 0 degrees C for water, the temperature stays flat even though you keep adding heat.
Flat? Why?
Because all that energy being added is going into breaking the hydrogen bonds, overcoming the intermolecular forces to turn solid ice into liquid water. It's being used for the phase change, not to increase the kinetic energy temperature of the molecules.
Ah. And then once it's all liquid.
Then the temperature of the liquid water starts to rise again as you add more heat until you hit the boiling point, 100 degrees C at standard pressure.
And then it flattens out again.
Yep, another plateau. All the energy goes into vaporization, turning liquid water into steam. Only once all the water has turned to steam will the temperature of the steam start to rise above 100 degrees C.
Those plateaus show the energy needed just for the phase change. That's neat. Is there a limit to how hot a liquid can get before it just has to be a gas?
Yes, there is. That involves the critical temperature and critical pressure. The critical temperature is the absolute highest temperature at which a substance can exist as a distinct liquid, no matter how much pressure you apply.
Above that temperature, it's always a gas.
Well, it's something else. A supercritical fluid. Above the critical temperature and critical pressure, the distinction between liquid and gas disappears. You get this state that has properties of both.
Like what?
It can expand to fill its container like a gas, but it has a density much closer to that of a liquid. This makes supercritical fluids excellent solvents. Supercritical carbon dioxide, for instance, is widely used.
For what?
Decaffeinating coffee beans is a big one. Also extracting flavors and fragrances, and in some chemical reactions, substances with stronger intermolecular forces generally have higher critical temperatures. It takes more energy to get them past that point of no return for condensation.
Okay, supercritical fluids. Another state to think about. Let's circle back to liquids and gases. What about things that evaporate easily, like rubbing alcohol or gasoline? You mentioned volatility.
Right, volatility relates directly to vapor pressure. Imagine a liquid in a closed container. Some molecules at the surface always have enough energy to escape into the gas phase. That's evaporation.
Okay.
As more molecules evaporate, they build up pressure as a gas, vapor, above the liquid, but some of those gas molecules will also bump back into the liquid surface and get recaptured. That's condensation.
So evaporation and condensation happening at the same time.
Exactly. Eventually, the rate of evaporation equals the rate of condensation. The system reaches dynamic equilibrium. The pressure exerted by the gas molecules at this equilibrium point is called the vapor pressure of the liquid at that specific temperature.
And volatile liquids.
They have high vapor pressures, they evaporate readily because their intermolecular forces are relatively weak, making it easier for molecules to escape into the gas phase. Gasoline, ether, acetone, those are volatile. Water is less volatile, motor oil is not very volatile at all.
And vapor pressure changes with temperature.
Definitely. Higher temperature means more molecules have enough kinetic energy to escape, so vapor pressure increases significantly with temperature.
Which leads us directly to boiling, right?
The perfect connection. The boiling point of a liquid is simply the temperature at which its vapor pressure becomes equal to the external pressure pushing down on the liquid surface.
Usually atmospheric pressure.
Usually, yeah. At sea level, atmospheric pressure is about 1 atmosphere, and water's vapor pressure reaches 1 attomella at 100 degrees C. So water boils at 100 degrees C.
But what about high altitudes, like Denver?
Good example. In Denver, the altitude is higher, so the atmospheric pressure is lower. Water's vapor pressure will equal that lower external pressure at a temperature below 100 degrees C.
So water boils cooler.
Yep. Which means food takes longer to cook because it's cooking at a lower temperature.
And a pressure cooker does the opposite.
Exactly. It traps steam, increasing the pressure inside. Now, water has to get much hotter, maybe 120 degrees C or more, for its vapor pressure to equal the higher internal pressure. So water boils hotter, and food cooks faster.
It all connects back to vapor pressure versus external pressure. Neat. Is there a way to predict vapor pressure?
There is. The Clausius-Clapeyron equation. It's a mathematical relationship that connects a liquid's vapor pressure, its temperature, and its heat of vaporization. If you know the vapor pressure at one temperature, you can use it to calculate the vapor pressure at another temperature, or even estimate the heat of vaporization if you have a couple of data points. Very useful tool for chemists.
Chemistry has equations for everything. Okay, let's try to visualize all these states and transitions together. You mentioned ice skating earlier and how pressure melts the ice.
Right, that's a great lead-in to phase diagrams. A phase diagram is basically a map for a substance.
A map showing what?
It shows the stable state, solid, liquid, or gas of a substance at any given combination of temperature and pressure. It summarizes all the equilibrium conditions between the phases.
So it's like a graph with temperature on one axis and pressure on the other.
Usually, yes. Temperature on the x-axis, pressure on the y-axis. And on this graph, you'll see distinct regions representing solid, liquid, and gas phases. The lines separating these regions show the conditions where two phases can coexist in equilibrium.
What are those lines called?
There's the vapor pressure curve, which separates the liquid and gas regions. That's the line showing the boiling point at different pressures. There's the sublimation curve, separating solid and gas. And the melting curve, separating solid and liquid, showing the melting point at different pressures.
And do these lines meet anywhere?
They do. All three lines meet at a single unique point called the triple point. At that specific temperature and pressure, all three phases, solid, liquid, and gas, exist simultaneously in equilibrium.
Wow, all three at once.
Yep. And there's another important point. The vapor pressure curve,
Yeah.
liquid-gas line, doesn't go on forever. It ends at the critical point, which corresponds to the critical temperature and critical pressure we talked about earlier. Beyond that point, you just have the supercritical fluid region.
Okay, so the diagram maps everything out. You said water's diagram is unusual.
It is. The key difference for water and a few other substances is the slope of the melting curve, the line between solid and liquid. For most substances, this line slips slightly to the right, meaning increasing pressure increases the melting point.
But not for water.
Nope. For water, the melting curve slips slightly to the left. This means that increasing pressure actually lowers the melting point of ice.
Which is why ice skating works. The pressure melts it.
Exactly. And it reflects that weird property that ice is less dense than liquid water. This unusual slope is directly related to that density difference. It also allows for things like freeze drying.
How does that work again?
You freeze the food, then lower the pressure way down below the triple point pressure. Then you gently warm it. Because the pressure is so low, the ice doesn't melt. It sublimes directly from solid to gas, leaving the dried food behind.
Clever. So what about something like dry ice, carbon dioxide?
Its phase diagram is more typical. The solid-liquid melting curve slopes to the right, but importantly, its triple point is at a pressure above standard atmospheric pressure, around 5 atm.
What does that mean for us at normal pressure?
It means that at 1 atmosphere pressure, solid CO2, dry ice, never melts into a liquid when you warm it up. If you look at the phase diagram, starting in the solid region at 1 atm and increasing the temperature, you cross directly over the sublimation curve into the gas region.
So it goes straight from solid to gas.
That's right, it sublimes.
Yeah.
Which is why it's dry ice, no messy liquid phase at normal pressures, great for cooling things without getting them wet.
Phase diagrams really tell the whole story. Okay, one last topic, something very modern. Liquid crystals, like in my phone scroll.
That's exactly. LCDs, liquid crystal displays are everywhere. Phones, TVs, monitors, watches. It's a fascinating state of matter that's sort of in between a conventional liquid and a solid.
In between.
Well, it started back in 1888. Friedrich Reinitzer was studying a cholesterol derivative, cholesterol benzoate. He noticed it melted from a solid into a weird, cloudy, viscous liquid at 1 temperature, and then at a higher temperature, it suddenly became a clear, normal liquid.
That cloudy state was the liquid crystal.
That was it. What we now call a liquid crystal phase or mesophase. It has some degree of molecular order, like a solid, but the molecules still have some freedom to move around, like in a liquid.
So partial order, partial mobility, what kind of molecules do this?
Typically, they are fairly large, elongated, rod-shaped molecules. They often have some rigid segments and maybe some flexible parts, and sometimes polar groups that help them align with each other or with electric fields.
And there are different kinds of this partial order.
Yes, several types based on how the molecules arrange themselves. In the nematic phase, the molecules tend to point in the same general direction, but their ends aren't aligned and they're not in layers. Think of logs floating down a river, roughly parallel but jumbled. Then you have smectic phases, where the molecules are still pointing in the same direction, but now they're also arranged in distinct layers. Smectic A means they're perpendicular to the layers. Smectic C means they're tilted.
More ordered than pneumatic.
Right. And then there's the cholesteric phase, often formed by chiral-handed molecules. Here, the molecules are in layers like smectic, but the direction they point rotates slightly from one layer to the next, forming a helical or spiral structure.
A spiral. Does
Yeah.
that do anything interesting?
Oh, yeah. That spiral structure can interact with light in very specific ways, reflecting certain colors depending on the pitch of the spiral. And that pitch can be very sensitive to temperature or pressure. So some cholesteric liquid crystals are used in mood rings or thermometers that change color.
Wow. And how does this work in an LCD screen?
Most common LCDs use a pneumatic liquid crystal, often in what's called a twisted pneumatic setup. The liquid crystal material is sandwiched between two electrodes and polarizing filters. When there's no voltage applied, the rod-like molecules are arranged in a gentle twist between the top and bottom surfaces. This twisted structure actually rotates the polarization of light passing through it, allowing it to get through the second polarizing filter so the pixel looks bright.
And when you apply voltage?
The electric field makes the polar liquid crystal molecules straighten out, aligning themselves with the field. Now they don't twist the light's polarization, so the light gets blocked by the second polarizer and the pixel looks dark.
So voltage on a dark, voltage off, bright up.
Or vice versa, depending on the setup, but that's the basic principle. By controlling the voltage to tiny individual pixels, you can create images. It's really a clever application of controlling these subtle intermolecular alignments with electricity.
It really is, from ancient Greek ideas about elements to manipulating molecules in our screens. It all comes back to these states of matter and the forces holding them together.
Absolutely. Understanding these intermolecular forces lets us predict properties like boiling points, viscosity, surface tension, and it lets us design completely new materials like ionic liquids or the liquid crystals that make our modern displays possible.
It definitely makes you appreciate the complexity hidden in simple things, like water boiling or ice floating. It's all this intricate dance of molecules and forces.
Makes you wonder, doesn't it? What other everyday things are secretly being run by these subtle, powerful intermolecular forces?
Something to think about. Thank you for joining us on this deep dive into liquids and intermolecular forces. We really hope you're leaving with a fresh appreciation for the chemistry happening all around you every day.
Until next time.